Good afternoon, everyone, and welcome to Beaumont Development Webinar Series. Today we will be discussing thermal pins, different modeling techniques, and how those impact the results. My name is Michael Hall, and I'm a design and simulation engineer here at Beaumont. Before we get started on some background and case studies, we can discuss a little bit of background about myself. Started at Beaumont Technologies back in 2013 in an internship role. Developed into a full-time position in 2016 when I graduated Penn State Behrend with a plastics engineering technology degree. Continuing up until 2020, where I achieved my Autodesk Moldflow expert certification and continue working with the engineering consulting team here at Beaumont Development up until present day. It's important to establish some background before we jump into the case studies regarding thermal pins. So what are thermal pins? And here I have listed several different names, some common interchangeable names here for thermal pins, such as cooling pins, heat pipes, heat tubes, isobars, copper rods, and copper pins, sort of all under an overall encompassing name known as thermal pins. And what thermal pins are a high temperature isothermic pin that allows for optimal heat transfer rates. Basically, they're used to improve cooling, and they're used in narrow deep draw features just like baffles and bubblers, and often used in conjunction with bubblers and baffles. But they're also used in cores, slides, lifters, etc. The main purpose and sort of what led us to start investigating thermal pins a little bit more is through emerging complexities of plastic parts. The difficulty to cool specific regions on these more complex parts is becoming more difficult. So more components are being transitioned from metal to plastic. They're becoming more complex, larger, tighter tolerances, etc. So we're forced to enhance our cooling techniques in order to meet those tighter tolerances. And that's where thermal pins are just becoming more and more popular in present day. So shown in the images below, I have a couple different configurations where we see some thermal pins. So here on the left-hand side, we have a couple thermal pins here. These are protruding from the end of baffle features. And then on the right-hand side, we have a similar setup as well, some additional thermal pins that are coming out of baffles as well. And these ones are a little bit more narrow, getting into deep draw regions. So from here, we can jump into how do we represent thermal pins in Moldflow? And this is an important thing to establish before we really go into case studies involving more thermal pins. And shown on the screen now is a part that we mocked up just in order to establish a couple different modeling techniques and determine which ones are ideal in terms of modeling thermal pins to perform their intended use. So shown on the screen on the left-hand side, we have a CAD body thermal pin representation, and then we have an extended baffle thermal pin representation. So when reviewing and examining thermal pins within a mold file, they can commonly be mistaken for an extended baffle. And it raises the question, as from a Moldflow perspective, if we were to model these as a extended baffle, set correct material properties, would we achieve similar results to actually representing them as a CAD body? Because modeling an extended baffle is just a few extra lines in terms of modeling, certainly a little bit quicker than a CAD body method. And if they yield similar results, then is this a valid study? Can we continue modeling with extended baffles? Does it make sense? So just some continued setup work here, showing the different configurations, how the thermal pins are penetrating into the deep draw features and the overall circuit layout. Some additional setup items here. CAD body, we set the CAD body to a mold insert surface, which I'll touch on more later. And we have pure copper properties set to all 6 thermal pins. For the extended baffles, as I mentioned, we model this as a traditional baffle. So two separate baffles, one larger, one smaller. Flow is going through both sections, and we have pure copper properties set to only the top reduced diameter portion, and the diameter was set to match the thermal pin CAD body. So what we're seeing here shown on the screen is the mold temperature output, and just made a note here where the cooling inlet is so we can kind of get a grasp of the results. And we'll focus on these deep draw features where we have thermal pins in both iterations. So first focusing on the CAD body method, left-hand side. As we look at the part geometry in general, as well as the deep draw features, we're seeing pretty uniform temperature load and actually lower temperatures in the deep draw features versus nominal wall. So we're at 197 versus 230, 225. And that continues throughout. So as we continue throughout the circuit, we shouldn't be seeing a temperature rise from inlet to outlet, at least from the thermal pin perspective, because they're supposed to be isothermic, meaning we're maintaining uniform temperature. So we can see that's taking place. So this CAD body method is sort of validating we are seeing temperature removal from the part. Thermal pins are doing their job. This method is working. Now, when we look at our extended baffle method, like I said, we match the diameters of the thermal pin CAD bodies, and then we also set the material properties to match the same as well. But what we're seeing here, once again, reminder, our coolant inlet's bottom left-hand corner, a constant temperature rise as we hit each deep draw feature. So we're going from 209, 218, continuing up to 220 as we come around the corner, 229, 230. So a takeaway here is the deep draw regions are not uniform due to coolant temperature increasing as it flows through the part. So these are behaving like a baffle would, kind of verifying that maybe this method isn't giving us the result that we're desiring for a functionality standpoint. So as we look at our next slide here, circuit coolant temperature, just to further investigate what's actually taking place in this extended baffle iteration. So CAD body iteration, just quickly here, 122 at our inlet, 125 on our outlet. So we have a 3-degree temperature rise, which seems pretty feasible based upon this circuit. It's pretty basic. We have 6 baffles, but it's relatively short, and we're rising about 3 degrees. This falls in line with what you would expect from typical results. When we look at our extended baffle iteration, we're ranging from 122 all the way up to 164. So about 40 degrees, a little bit more than 40 degrees, temperature increase from inlet to outlet. Certainly not ideal and acceptable in terms of a typical coolant circuit plot. And we're seeing as we flow up each extended baffle, we're gaining temperature. And this simply just isn't achieving what we would expect from the functionality standpoint for what a thermal pin is intended. So what this leads us to from a conclusion standpoint is that modeling thermal pins as an extended baffle is not giving us results that we would like. And the results are not making sense as to how a thermal pin is supposed to function. So this CAD body method is really what we want to focus on moving forward. So what we're going to investigate a little further here in our next case study is we're going to show, have a cooling line study that's already modeled. So we'll examine that. And then we're going to look at how to import and mesh these copper pins. We'll set the pin properties and then simply import those pins into the final cooling study. So let's take a look here. And we'll open up that cooling study. Rotating around here, we can see inlets, outlets, part geometry, hot manifold system, as well as our baffle features. What we need to do next is add our thermal pins. So we'll jump back here, and we already have a file that includes those thermal pins called the simplified cooling. And we'll change our mesh type to dual domain and go ahead and import those. So now that we have that study imported, we can see our 5 different thermal pin locations, and that's really the only thing that we need from this study. So we're going to go ahead and grab those thermal pins and assign them to their own layer. We'll just call it pins, assign, and we're going to hide that layer. So like I said, we already have everything in that other study that we need, so we'll just go ahead and get rid of all this. Delete, clean layers, and that'll just leave us with our pins. So the next step would be to put a mesh on the pins. And these don't need to be complex from a mesh standpoint. It can be pretty basic. We're going to stick with our default mesh settings here. Uncheck match mesh because we're not predicting flow through these. So like I said, it doesn't have to be a very tight mesh or anything. We'll leave auto sizing at 1, keep the edge length where it is, just mesh it, see what it looks like, and we can make some adjustments from there. So as those pins are meshed, we can take a zoomed in view here, and mesh looks pretty good. I'm not going to make any changes to this. It's acceptable for surface mesh on thermal pins. Next step is to highlight all the pins, change property type, and we're going to change to mold insert surface. As we click OK here, we're going to move forward to changing the material properties, which, as I mentioned earlier, we're going to look at a pure copper pin. So we'll make that selection as well. The last change we'll change here is just a simple personal preference, and we'll make these solid display so that they're a little bit easier to see in final assembly. Save our changes, and we're ready to add to our cooling line study. So we pop that study back open, and we'll go ahead and use the add function here. Add our simplified cooling study. And when that drops in, you can see thermal pins are in place. So this setup method is pretty simple. In this case, there's only 5 pins, so it's not very complex in terms of, or time consuming for that matter. And it's the same general setup regardless of what material properties you're using. So in the case of an isobar or something like that, the only difference is you would change the material properties to an isobar instead of pure copper pin. So relatively simple setup there from the CAD body perspective. Our next portion of the case study is to investigate thermal pins, but it's important to first focus on and establish a baseline correlation between dual domain and 3D. So we have our BEM cooling modeling technique, and then we have dual domain part versus 3D part. Neither study has thermal pins. So this will just allow us to confirm that they're trending the same for this part geometry. And when we look at mold temperature result, once again, we can see dual domain part and 3D part are very similar from a mold temperature standpoint. Due to the deep draw feature within this part, we expect a hotspot to take place here. And we can see, just focusing on these main 3 values here, they're very similar between dual domain and 3D. So this verifies that dual domain and 3D are trending similarly, and it's an important verification step. So when we're looking at our studies moving forward, we have this in our back pocket. So as we progress here, still using BEM cooling, and that last slide we looked at, we're carrying over this dual domain part, no thermal pins, as our baseline comparison study. Top right hand corner, we have a dual domain part with dual domain thermal pins. So this is similar to the setup that I showed in the Moldflow setup. Bottom left hand corner, we simply converted part mesh to 3D, kept these pins dual domain. And in the bottom right hand corner, we have the 3D part and 3D thermal pins. So simply converted those 3D thermal pins to 3D as well, and then set those material properties. So how do these studies compare from a temperature perspective? Just taking a quick look here at our thermal pins and non-thermal pins. When we look at our mold temperature plot, once again, dual domain part, no thermal pins, this is our baseline study. We can see our hotspot here. top right hand corner, dual domain part, dual domain thermal pins, we can see the temperature load is being pretty uniformly removed from that area. So what this tells us is that dual domain thermal pins are doing a nice job of removing heat from the part surface. Same can be said for the 3D part with dual domain thermal pins. We can see this hotspot is mitigated once again, and the values are very similar between this study and the top right hand corner study with dual domain pins and a dual domain part. So very similar results here. And in this last study, bottom right hand corner, we have the 3D part, 3D thermal pins. And we can see this hotspot is mitigated versus our baseline iteration, but there still is some temperature load taking place here. And what this is telling us is that the 3D pins are removing some heat from this area, but not as much as the dual domain pins, which is an interesting result. So when we take a breakdown and try to draw some conclusions from the BEM cooling results, first takeaway is that dual domain thermal pins remove heat from the part with both dual domain and 3D meshes. And when we take a look at our average temperature, specifically in that deep draw feature, we can see they're very similar between dual domain part and 3D part with the dual domain pins. The outlier here being when we have a 3D part and have 3D pins, our temperature is a little bit higher compared to the dual domain pins. However, it's still removing heat versus the baseline study. So those pins are still working and extracting heat from the surface, just not to the same level as the dual domain pins. So that's an interesting note we can discuss in our results later here. The next case study would be examining FEM cooling. And what is the difference when we have thermal pins in terms of modeling for FEM analysis versus BEM? So shown on the left is this study we've been using throughout our BEM method, where we have thermal pins, and you can see they extend above and below the baffle, which is fine for a BEM analysis in terms of modeling those thermal pins. However, when we look at the FEM method, it's important to note that these pins need to be cut at some point within the process in order to correctly be represented within the simulation. So whether that be your CAD package, you can do it in Fusion, you can make the cuts even in a simple plane cut from Moldflow if you're able to get a flat surface in order to use that cutting plane. But any number of ways to cut that thermal pin at the top of the baffle so that those can properly connect in the FEM mesh is certainly acceptable. So once again, just making a note that these pins are cut at the top of the baffle, whereas in the BEM analysis, we were able to leave the thermal pins as whole. So just an example, if you were to take these thermal pins and leave them extending beyond the baffle and take that to an FEM mesh, what that would actually look like. So you would have that baffle, or I'm sorry, the thermal pin extending well below the baffle feature and have overlapping surfaces at both the top and the bottom. So that's certainly not ideal in terms of an FEM analysis. There'd be quite a bit of manual repair required to get that to work. A much preferred methodology would be cutting those like we discussed on the previous slide. So having that simple cutting plane there allows us to have a much more uniform and easy repair from an FEM perspective. So you can see those pins are cut and they're sitting right on top of the baffle features. And just some additional setup tips here. When we're using the FEM thermal pins, even in that study where I cut the thermal pins and you put a mesh on it, you can see that Moldflow is just trying to stitch over the interface between these two components since they're not merged components. And we need to recognize this and repair all of our thermal pins. So what we're doing is just deleting this area around and connecting these thermal pins. So that's something important to note during our setup. We need to make sure that these are connected. An alternative option would be to merge your CAD bodies if you're able to do that within Fusion or your CAD package. if you're able to merge your baffle to your thermal pin before you import into Moldflow, then you could skip this step because they'd be one solid body already. But this is just one of the ways to do it. So now that we're looking at our FEM cooling, we need to establish that same correlation that we did with the BEM cooling. So we have our dual domain part with no thermal pins, and then we have our 3D part with no thermal pins. And we want to compare these results to ensure that they're trending similarly to move forward with one of the iterations. So on the left-hand side of the screen, we have the dual domain part, no thermal pins. We can see uniform temperature load across the part, which is a little bit odd because we saw a deep draw temperature increase in this area. And we see a abnormal temperature load of about 150 degrees taking place on this portion of the part that we didn't see in our BEM analysis. So this is a little bit of a questionable result. Looking over at our 3D part with no thermal pins, we can see a much more uniform temperature load versus the dual domain part. So this led us to investigate a little bit more from a study perspective. Why is this dual domain part behaving this way in an FEM study? So as we further investigate, we're just adding thermal pins to this. So we still have our dual domain part, we're adding dual domain thermal pins, FEM cooling. And is that going to do anything to this hotspot? What's causing that? As we look at our results, we can see that they're basically identical. So no thermal pins or dual domain thermal pins. We can see that this dual domain part is giving us some questionable results. So what this is leading us down the road to is for our FEM setup, the dual domain part mesh is not giving us reliable or realistic temperature results. So we're going to throw these studies out and we're going to use the 3D part mesh moving forward for our FEM setup. So when we look at our 3D parts only, left-hand side, 3D part, no thermal pins. Center iteration, 3D parts, dual domain pins. And then on the far right here, 3D part, 3D pins. And we'll look at the temperature load across the part in these iterations. So on the far left-hand side, we have that baseline study we already reviewed, and we can see that temperature load in the center of the part geometry. When we refer to the center iteration, we have a 3D part with dual domain pins, and the temperature is nearly identical across the part in this center iteration versus no thermal pins. So what this is telling us is that our dual domain thermal pins aren't removing heat from the part surface either. So from an FEM perspective, this is leading us down the road of this far right iteration where we have 3D part and 3D thermal pins. So once again, that temperature spike is still there, but it's reduced versus the baseline study. So what this is telling us is that the 3D thermal pins are removing heat from the part surface. To summarize and draw some conclusions from our FEM results, FEM part temperature results are questionable with dual domain mesh. Like we saw in the results, whether or not you have thermal pins, we're still getting questionable results. So we're not using that as a reliable modeling method. For the 3D part mesh, our dual domain pins are not removing heat from the part surface either. So that study is not giving us reliable results as well. The only setup method that's giving us uniform and reliable results is the 3D part with 3D thermal pins. They're removing heat from the surface versus the baseline iteration. So that's giving us the intended results of thermal pins. So lastly, an overall summary of results. What are the results telling us here? So from a BEM perspective, our dual domain part with no pins, we're right around 135. As we add dual domain pins, whether it be a dual domain or 3D part mesh, we get very similar results in terms of temperature extraction. And then with our 3D part, 3D pins, we're falling somewhere in between. The 3D pins are not removing as much heat load as the dual domain pins. However, they're still removing heat from the part geometry. So what this leads us to is with which methodology and setup is correct. In order to determine this, we would need some mold validation studies. From an FEM cooling perspective, as we mentioned, the dual domain part geometry setup is not a reliable method. The 3D part with dual domain pins is not removing heat from the part surface. So we rely on the 3D part with 3D pins, and that's removing heat from the part surface as well. At this point, we'll turn it over to questions. I put my contact information here, email as well as my direct line. If there's any questions that pop up after the review, feel free to reach out. Also included is the Beaumont Moldflow support contact information. Any questions that you may have on licensing or further information regarding Moldflow, please feel free to reach out to the support contact as well. Thank you. I appreciate your time today.